Okay, so just as an announcement, I have posted example survey papers to CCLE. Please make sure to check them out so you can see what format your paper should look like. And also, I would like to encourage everyone to start early. As for this class, the homework 3 I just assigned is supposed to be the last homework. So then you will have time to work on your survey paper. So it is important to choose a topic of your interest, hopefully related to your research. Then you will not feel like this is a waste of your time. And then you can review literature. I think the only requirement is that it must be related to large sample theory. So then we will look forward to your presentation in the last week so we can see what topics each other choose. And I think that will be very interesting. So I think doing so will make this final paper more related to your research. That's the hope. Okay, so today we are going to continue talking about the application of the delta method to derive some distribution of some sample moments and the sample correlation. So just as a reminder, let's say that we have this general result for the delta method. So I'm going to skip the conditions, but just write the result. So this needs to be a very nice continuous function g. If it's not continuous, at least it needs to have a continuous derivative near the neighborhood of mu. That's the minimum requirement. But for all the cases we have seen, the g is just continuous. And we have, sorry, I need to say this first. We have xn converges in law to x. So then the delta method is talking about the convergence in, okay, my bad, minus mu, convergence in law to x. Then this delta method is talking about the result after this g transformation. And we know it's going to be g dot, the derivative or gradient, depending on the domain and range for g times the x. Okay, the version we use most often is the normal version. So let's say if x follows a normal distribution with mean zero vector covariance matrix sigma, then this transformed x will follow normal distribution, still mean zero, but this zero may not be of the same dimension as here, depending on what dimension this g dot is. And g dot mu times sigma times g dot mu transpose. Okay, this is the delta method, the general result. And last time we talked about how to derive the distribution for the sample variance. So we have the sample variance denoted by this sx squared, and here it is about one-dimensional xi's. So let's see, x1 to xn are one-dimensional. Then this sx squared, the sample variance, we define it as this, sample variance. And we know that we can write it as the average of squares minus the square of the average. Okay, so therefore, to obtain the distribution of the sample variance, we use the delta method, okay? And we give this a notation. MXX, it stands for mean, sample mean, and XX means it's square minus mx squared. And in the example we have seen before, we first derive the asymptotic distribution of mx and mxx minus its expectation, which would be mu using our notation. And this is mu squared plus sigma squared. So I'm not going to do the derivation again, just a recap. Converges in law to some normal mean two-dimensional and some covariance matrix. Okay, it's a 2x2 matrix. I'm not going to spell it out. But this result is from CLT, central limit theorem. And then given the delta method and given the relationship between Sx squared, sample variance, and Mx and Mxx, given this relationship, we will apply the delta method to obtain. So we will have Sx squared, which is basically a g function of Mx and Xx minus sigma squared, which is basically the g function applied to mu squared plus sigma squared. Okay, this will converge in law to some normal distribution, zero mean, and some covariance. Okay, which I will not write out. But you know, this shows an example about how to derive the asymptotic distribution of the sample variance based on the central limit theorem. So central limit theorem will give us the moment as the sample means or sample averages. And given those moments, we can obtain the asymptotic distribution as some combinations of the moments. So here the sample variance is just a combination of this squared average and the average. Okay, so going forward, now let's look at paired random variables. Okay, so now let's think about our sample as written as paired x1, y1 to xn, yn IID. And here, we still consider x, y, yi to be scalar value, one-dimensional. Okay, and in this condition, we just need to add one condition, that is the fourth moment of xi and yi, fourth moments, they are finite. So we need this to ensure the following result. So first of all, based on this idea, we can actually obtain the joint asymptotic distribution for the sample variance of x, the sample variance of y, and the sample covariance of x and y. Okay, so same as before, the sample variance is defined as okay, and same for y. And the sample covariance we write as xy is this cross product, xi minus xn bar, yi minus yn bar. Okay, these are the sample variance and sample covariance. Why do we need this? The reason is because a quantity we use a lot called Pearson correlation coefficient, which can be computed based on these NIID random variables based on our sample, right? The sample of size m. This Pearson correlation coefficient at the sample level, okay, I call that R, is just defined as Sxy divided by Sx and Sy. So we don't have square anymore in the denominator. It's the square root of this, square root of this. That's the sample level. In other words, given n paired observations, we could compute a Pearson correlation at the sample level. At the population level, what is that? This will be based on the joint distribution of x and y. So let me just write that as rho. So you see, we usually use the uppercase letters, non-Greek letters for our statistics as a function of our sample. And we often use the lowercase Greek letters to denote the population parameters, like mu sigma square, and we're sticking with that. So this will be the covariance of xi and yi. Or I can drop I and just use x and y as the general notation. Variance of xi square root, variance of yi square root. This is the population Pearson correlation coefficient. So here, if we want to derive the asymptotic distribution for the sample Pearson correlation, our intuition would tell us the center of this R, asymptotic mean, should be this row. Just like here, the asymptotic mean of the sample covariance is the population covariance. So that's our guess, but how do we derive it? So first of all, here, the derivation is not difficult, but just tedious, okay? So first of all, we need to realize that this R can be written as a function of sx squared, sxy, sy squared. Similarly, this rho can be written as, so let me try to give this a name or notation. Okay, so let me think, what notation would be appropriate? So probably I would just write this as, okay, I'll just give another line. I'll write this as rho sigma xy for the covariance. And this is sigma x, sigma y for the standard deviations of at the population level. So by the same argument, this rho will be the g function of sigma x squared, sigma xy for the population covariance, and sigma y squared. That's it. So based on the delta method, as long as I can have the asymptotic distribution of the sample variances and covariance, sx squared, sxy, sy squared, minus its population version, sigma x squared, sigma xy, sigma y squared. As long as I can know that this joint asymptotic distribution is a three-dimensional normal, okay? This will be a 3x3 covariance matrix. As long as I can have this, then I can use this g function and the delta method to obtain the asymptotic distribution for the sample correlation coefficient, which would be R minus rho converging log to a normal distribution with zero mean and some variance. I know that will be the result I get. Okay, so now coming back to the root, how do we get this joint asymptotic distribution for the sample variances and sample covariance? It's basically the same problem as here, okay? It's just here we're doing sx squared alone. Here we're going to do sxy, the sample covariance, as well as the sy squared. Okay, so basically, we're going to use this relationship that is sx squared, we have this already, right? mxx minus mx squared, right? We have that definition. Similarly, we can write xxy. The sample covariance, I can write it as mxy minus mx times my. So the notation has the same format, okay? So basically mxy is just the average of xi, yi, okay? Minus xn bar times yn bar. That's it. This is a way to calculate the sample covariance. And then sy squared is myy minus my squared. So basically, you see that the three things jointly put into a vector, it can be written as some function. I'll just denote as some h function of those moments, okay? So I just need to have mx, mxx, okay, my, myy, and mxy. I need those 5 moments. Then I can define this So with that 5-dimensional vector, I can obtain a 3-dimensional vector for the sample variance, sample covariance, sample variance. Okay, so this is the first step of delta method. I'm going to go, so central limit theorem will give me the asymptotic distribution for this because they are all averages of IIDs. From central limit theorem, I got asymptotic distribution for this 5-dimensional vector. Based on delta method, I get the asymptotic distribution for this 3-dimensional vector. And then based on delta method again, I obtain the sample correlation asymptotic distribution. Does that make sense to everyone? Just two steps or 2 applications of the delta method. Okay, so simplify things. To simplify things, we can show that, interestingly, if these IIDs are Gaussian, okay? So under the special case that these IIDs, let me try to erase this part. So if these are IID Gaussian, I just put the general mean and sigma square notation here. And, oh, sorry, my bad. I should say 2 dimensions, my bad. So if they are 2-dimensional bivariate Gaussian, I should put mean as mu x, mu y. And the covariance matrix, I can write it in this way. Sigma x squared, sigma y squared as the 2 marginal variances. And for the covariance, I can always write it as the correlation, population correlation times sigma x, sigma y. Correlation times sigma x, sigma y. Okay, so you see, I just need 5 parameters to specify a bivariate normal, the 2 means, 2 variances, and the correlation. Okay, and then given this, I can do what I said, by applying the delta method for twice, and then the final asymptotic distribution for the sample Pearson correlation will be super clean. It will take this form. See, it's only about rho. And what does this tell us? You see, that except when this rho is 1, when the x and y are perfectly correlated, right? Except when that happens, I will have a degenerate variance, variance equals 0. Except that I would have this asymptotic distribution that changes as this changes. Okay, so basically the closer rho is to 1, then the smaller this is. So it basically shows that the asymptotic distribution will have a smaller asymptotic variance. So what does it mean? It means that if the 2 random variables have a stronger population correlation, then we can have, when we estimate it by the sample correlation, we have better confidence. So the sample correlation is closer to the population correlation in the with the uncertainty bared in mind. Okay, so this is a super nice result. But still, you know, when we want to apply this result, and then we can apply this result to construct confidence interval for our rho, right? We just need to make sure that we have the confidence interval based on this distribution. And the confidence interval, just as a reminder, I think that's a very confusing concept on its own. So under the frequentist framework, when we say confidence interval, if we denote the 2 ends as, say, I'll just call rho hat upper bound, rho hat, oh sorry, lower bound, rho hat upper bound. Okay, if I denote in this way, the thing to keep in mind is that the confidence interval itself is random. Okay, the parameter is, we aim to cover it with the interval. The parameter in the frequentist sense is fixed, but the interval is going to be constructed from the sample, so it is random. So what we can say for, say, 95% confidence interval means that this confidence interval as a random interval, it has 95% of chance to cover this true parameter. So to construct this, we are going to utilize this distribution of R because R is the random variable here, the statistic. We will utilize R to find what's row had lower bound, what's row had upper bound. Okay, but that's not the focus here. What I really want to say is that given this distribution, to find the confidence interval for rho, an issue we need to deal with is that the asymptotic variance involves rho. So therefore, it's likely that these two bounds will involve this unknown rho, and that's not desirable, right? In order to have a confidence interval computable, it should not involve unknown parameters. And that's the issue we need to address here. Okay, so one thing called variance-stabilizing transformation is to deal with this issue. So the goal is to make sure that the asymptotic distribution doesn't involve any unknown parameters after the transformation. Okay. And we're going to use delta method again to help us with this. So you see, the goal is to find some transformation G using this example, okay? In this example, because we have the scalar value, I'll just say G maps from R to R, such that with the delta method applied to this result, GR minus G rho converges in law to a normal distribution 0 mean, and then I would have G dot rho, the derivative, because it's scalar, I can just square it times the variance. Okay, so the goal is to make sure this asymptotic variance not related to rho anymore. So we want this to be irrelevant to rho. And of course, the simplest way to make it irrelevant is to set it as 1. Okay, so set G dot rho square times 1 minus rho square equal to 1. Solving this, we can easily see that G dot rho, the derivative, will be 1 over 1 minus rho square, right? And this is something many of us must be familiar with if you know like 1 minus rho square is equal to 1 plus rho times 1 minus rho, right? So we can easily see that this is equal to 1/2 1 over 1 minus rho plus 1 over 1 plus rho. You can easily verify that they equal to each other. So this is the derivative. Now we want to go to G. From the derivative, find the G by integration. And this is not difficult because these two functions are can be easily integrated. So we can easily show that it will actually, the G rho would just be 1/2 log 1 plus rho divided by 1 minus rho. So we can easily verify that ourselves. I'm just doing the combination. So this will give me a log, this will give me a log, 1 is minus sign here, and combination give me this. Okay, and with this G, I can obtain a nice result for my sample correlation. So basically, you see, applying this G with the delta method, what I have is 1/2 log 1 plus the sample correlation divided by 1 minus sample correlation minus 1/2 log of 1 plus rho population correlation divided by 1 minus rho. This thing would converge in law to standard normal. So now with this, and to construct the confidence interval of rho, right? I can start with some confidence interval for this quantity, and then I do some algebra to simplify it to make sure it's an interval for rho. So, but with that, I'm just able to make sure that the confidence interval will not involve the unknown parameter rho anymore. So you see, this is the advantage. So to make sure the asymptotic distribution part doesn't involve any unknown parameters. And this is usually called the Z transformation of sample correlation. And you can see that by doing this, log R itself is between -1 and +1 by definition. And you can see that by doing this transformation, this log ratio will be real value. Okay. So you can see these are very interesting applications of the delta method. So last time, the delta method we talked about is based on first order Taylor expansion, or we can say mean value theorem. And we did see a case where the asymptotic variance degenerates, right? So for the x bar square, remember that its asymptotic variance will involve the mu square, and if mu is 0, then it goes to 0. So therefore, we have to go to the second. In that time we didn't do the second order Taylor expansion, but what we did is to apply that Slutsky theorem with a continuous mapping, right? So basically, we know the square of a standard normal will be chi-square 1. We use that result to fix it. But now we're going to give you a more general result about what happens to the delta method when we go to the second order for our Taylor expansion. Okay, great. So I'm just going to write out a second order approximation of Taylor expansion. Again, we're going to start with the function g first. So for simplicity, we just assume the g function to be just one-dimensional to one dimension. And also it has second order derivative continuous in the neighborhood of mu. Because we need a second order, so we need a second order derivative. So with this, we can write by approximation that, okay, is approximately first derivative at mu times x minus mu, right? Plus second order derivative at mu. This. Okay, this is we ignore the further terms. And recall that the term we are interested in is these two. So recall that the reason we want to use this G for transformation is because CLT tells us root n times xn bar minus mu will converge to some normal, right? And we want to know, our question is, what is the distribution of, sorry, I should write it. I should write the complete version. Okay, so this tells me this. Okay, so what I basically, by dividing sigma to this side, and I will have this converge in law to standard normal. Okay, I start from here. I'm going to use this result. So the question we are interested in knowing is we will transform G, apply G to xm bar and G to mu. And we are interested in knowing what happens to this, right? And so that's why we do the delta method for that. So basically, you can see that if I replace x by my xm bar, Okay. Okay. These stay the same. Okay. I have these. Okay, but these doesn't tell me much yet because only this term after multiplying by root n divided by sigma, I get a nice standard normal. And I need a standard normal to play with the square, those kind of things, because standard normal has very nice properties. Its square is equal to chi-square 1. So to use that property, what I'm going to do is to do, okay, if I do this, and let me see, correct. So then, actually, I think not enough. Sorry, my bad. Okay, not enough. I'll stop doing it for now. This is okay. Okay, on the right-hand side, what I'm trying to do is that I'm trying to create a square term for x n bar minus mu, because this is what the CLT tells me about. So I'm trying to combine the two terms to create a square term. So I'll just go quickly and see, and you guys can see that if I create a term, then what I would do is that I will have this g second derivative at mu divided by 2. Okay, and inside, if I'm going to create a square term based on this, let me just first write it down. Root n x n bar minus mu sigma divided by sigma plus root n, I'll just write it, g prime mu sigma g double prime mu. Okay, this is the first term, and I will have a second term, maybe just minus this n times g dot g prime mu square divided by sigma square g double prime mu square. Okay, so with these, let me erase this part. Okay, so with this, then I need to have sigma square, right? So basically you see that I'm having the sigma square here to cancel with the sigma square here. I'm going to have a sigma square in the denominator inside the bracket. That's going to be canceled by the sigma square in the numerator outside. And what else is actually basically the same, except the introduction of root n in the square, and which becomes n out of the square. So this will give me n times the left-hand side. Okay, and actually the right-hand side, I know what the distribution is, because this is following convergent to law, I should say, convergent to law to standard normal. And this is a term that only depends on sample size n and the g functions, derivative, first order, second order derivatives, mu and sigma. So I can give this a notation gamma n. So I need n here to mean the sample size. Then this is just gamma n squared. So then what I know about this is that for standard normal distribution, we first shift it to the left by gamma n, and then we squared it. So we know that this is known as so basically this term is known to converge to a non-centric or non-central chi-square distribution, still chi-square 1, but shifted by this gamma n squared. That's what we mean. So essentially, if you have a standard normal, you shift it by gamma, and then you square it. This is known to follow a non-central chi-square 1 distribution with the shift denoted by chi-square n. Okay, and then this term says that with a random variable following this distribution, we shift it back by chi-square n, by gamma n squared. Okay, and this is just a constant term, multiplying this. So in other words, what we have here is to derive an asymptotic distribution for the transform statistic minus its transform mean, but not multiplying by root n. That's the first order delta method. For the second order delta method, we multiply by n. So this is a heavier, or I would say the larger, this is a constant that goes to infinity much faster to counteract that this may go down to 0 faster than root n. So giving a root n is not enough, so we give an n. And in that case, we have this asymptotic distribution. And what happens, you see, when we have that result for the first order, let's compare the two. Recall the first order is this. We just saw it. Normal distribution, 0 mean, g prime mu square times sigma squared, right? That's the result we have seen before. And when does this result fail or degenerate? It's when this term is 0, right? This degenerates when g prime mu is 0, okay? And when g prime mu is 0, what happens here? It's actually doing us a benefit. When g prime mu is 0, that's gamma n will actually be 0 because it has g prime mu in the numerator. Then this limit, the second order limit, would just become chi-square 1. And that's exactly the case we saw in the previous example. When we have the degenerate case, we have to go to the second order. We apply the Slutsky theorem with the transformation square, and then we have chi-square 1. That's it. But then but you can see that the whole derivation for the second order Taylor doesn't require this g prime u to be 0, right? This holds in general. Then you may wonder how close this is to this, right? We will wonder this, right? But the thing that's very nice is that we can actually show that for this distribution, okay, when this gamma n, the shift is large, which translates to the fact that this term is, or actually we do have gamma n goes large because, you know, we have a root n here. So when n goes large, gamma n goes large, right? And we can show that this non-central chi-square 1 shifted back, it will actually follow a very similar to normal distribution. So it's actually approach a normal distribution. So in that case, we do not have any inconsistency between using this result and this result. So in other words, when this gamma n is large or this g prime mu is large, we can use this first order without problem. But when this doesn't work, then we have to go to the second order to make sure we have some non-degenerate distribution. That's pretty much it. Okay. Oh, one more thing I forgot to say. When I say this is getting closer to normal, we need to think about here, we multiply root n additionally, right? It should be just root n is enough, but here we multiply it by another root n. So that's why this distribution is also divergent. So that's why we need to cancel that out. Okay, so these are all I want to say about the delta method. Do we have questions before we move on to the next topic? Yeah. I would say that it's not easy to do it based on the asymptotic distribution, right? because this result only holds, or this distribution only holds well when you have a large n. If you don't have a large n, this distribution may not hold well. So using it to derive the confidence interval will have a problem. But I think for some cases, if you want to do some correction, then I believe you need to make some assumption about the data distribution first, and then you can do that. And also, I would say you may also use this second order Taylor expansion to get a more accurate result, right? But still, I have to say that even for this one, you are still looking at a large n, so that when n is large, so you can ignore the following terms. Yeah, so that's why, you know, nowadays with computer, since the 1970s, 80s with computer, a lot of times people can use bootstrap instead of using the asymptotic confidence intervals. This was the old days, the old technique when you don't have computer, right? You have to have something easy to compute, and that's your best approach. But nowadays with the computers, you can do some computer intensive ways to derive better finite sample confidence interval. And I think that was the reason why bootstrap was really a hit back in the 1970s, 80s, because people showed that, yeah, it can give you better inference, right, for finite sample size. All right, but still, I think asymptotics makes sense when you want to save computing time, right? Because it's so fast, it gives a closed form formula. When it works well, you should use it. Okay, so with this part wrapped up, and that's a very nice question, we will go into a new topic called order statistic. So order statistic, I found itself to be highly useful because, you know, a lot of times we prefer to use more robust statistics. And one case of that is median is more robust than the mean, right? It's less affected by the outlier. But to define the median, you need order statistic. You need to order your n sample, right, observations, x1 to xn, sort them from smallest to largest and pick the middle. That's the median. So that's why we are going to talk about order statistics first, and then we will talk about sample quantiles, which are based on order statistics. So the first thing we will talk about to start with, we'll talk about extreme order statistics. So what do we mean by that? So given an IID sample, based on our writing, x1 to xn. So we sort them from the smallest to the largest. We will write with a parenthesis around the index. Okay, and this is the minimum, and this is the maximum. And please note that even though x1, this ordered x parenthesis 1, doesn't look like it depends on n, but it actually does, because we need to have a sample of size n to sort it. So therefore, this xn will actually depend on the whole sample x1 to xn. So that's why, you know, sometimes to make it exactly clear, people may write this notation as something like this, the second one like this, to carry the n with it. So you bear in mind that it depends on the sample size. But this one is more common, this notation. Okay, so by extreme order statistic, we mean that we are interested in the statistic closer to the two ends, the minimum or the maximum, or the second minimum, the second maximum. So we're going to talk about their distributions. And to do that, the key is to use this interesting result, a limit formula from calculus. So this is about a fixed constant c, okay, fix the c, And then if we have 1 plus c over n to the power m, this formula, we know it has a limit, and the limit is just exponential c as n goes to infinity. So this, and then you know the limit has nothing to do with n anymore, and that's what we want. So we are going to use this result a lot in our derivation of the asymptotic distributions for the extreme order statistics. And we can make this result a little more general. So let's see that if we have the more general version, is that the C may be a sequence, a convergent sequence, and this M may be replaced by a divergent sequence. So that means if we have this Cn over Bn to the power Bm, so if Cn converges to C, a fixed C, and Bm diverges to infinity, if we have both, then we still have a limit for this. It's still exponential C. So these two results will be the key mathematical component for our following discussion about how to derive the asymptotic distribution for the extreme order statistic. So we'll just do several examples for this part. The first part is we have x1 to xn IID uniform 0 to 1. So in this interval. So we will see later why we want to talk about this uniform 0 to 1 interval a lot. The primary reason is that for any random variable that follows a distribution f, if we know the CDF function f, then we apply f to the random variable, then that random variable will be uniform 0 to 1. So that means if we have this result for uniform 0 to 1, and we know that the CDF function is monotone, increasing, and also its inverse, f inverse is also monotone, right? So therefore, the maximum before transformation or the maximum after transformation will still be the maximum. So that's why we can easily talk about the extreme order statistics distribution for other distributions if we know how to do this for uniform one. So that's why this provides a foundation, because we can easily obtain other random variables from uniform 0, 1 random variables. And that's actually how our computer does the generation. If you want to generate Gaussian, exponential, actually the random number generated in the computer is uniform. And then you can create draw other values. Okay, so the question we will address here is, what's the asymptotic distribution of the maximum xn? Okay, so first of all, we need to have some nice guess. Okay, so if you look at what we have here, for this asymptotic distribution we have seen so far, like the CLT, we know that we first know xn bar converges in probability to mu by law of large numbers, right? So that tells us xn bar minus mu, just the difference itself, will converge to 0 in probability. But we want to stabilize this so we get a distribution, not 0. So we need to multiply by some divergent constant that increases with n. And we found that, okay, so this can be changed to a normal distribution. Okay, that's primarily what the central limit theorem does. So for this example, if we can also find, okay, what does my extreme order statistic converges to without multiplying the divergence sequence, then I can figure it out. Okay, so let's first see that. So then what will be your guess? Xn, the maximum, in this case, What does it converge to in probability? Yeah, 1, exactly. This is very natural, right? You know that when you draw a sample uniformly from 0 to 1, the larger the sample size, the closer the maximum will be to 1, right? That's our intuition. And let's verify that. So we'll just use the definition. What is the probability that this is greater than any epsilon? Okay. And we know one nice thing is that the xn maximum can never be greater than 1. So we know this must be negative, right? Inside the absolute value. So it means that it's the probability that xn is less than 1 minus delta. It can only go one direction, not the other direction. So now this is something I think most of you should have seen in undergrad class. So when the maximum is less than 1 minus epsilon, it means that every xi is less than 1 minus epsilon. Because of the IID, we can have that joint probability factorized as the product of each one's probability, right? And that's just the xi's probability raised to power n. That's it. So okay, and so basically this is the probability of x1 less than 1 minus epsilon raised to the power n. And that's just 1 minus epsilon to the power n. Obviously, this goes down to 0 as n goes to infinity. So we use the definition of convergence in probability to prove that 1 is indeed the, is indeed the limit in probability for my maximum. So I now have this degenerate result, but I'm not happy with this because this doesn't tell me the distribution. So the question to figure out is what divergent constant I need here. So we have seen root n, we have seen n, right? So it must be something related to n. So to figure that out, I would just say, okay, how about I consider sequence an, okay, that diverges with n, such that if I do an multiplies, maybe I will do 1 minus xn. The reason I reverse the order is because I want to have something positive, because xn is always under 1. Okay, I want to find what is this an such that this thing will converge in law to some non-degenerate distribution. Okay, this is the puzzle we will solve all together. And let's do that. So in order to do that, we will try to first, so carry this an with us. It's just a constant sequence. The first thing we will do is try to derive the CDF function of it. So hopefully the CDF function, given that this maximum is the maximum of uniform 0 to 1 IID, we can have the CDF just as some function of n. And then we will see when does that CDF function be non-degenerate. That's our goal. Okay. So because if it's degenerate, then the CDF function will be the CDF function of a point mass 0. And we know what it is. That CDF will be 0 before reaching that point mass 0, and will suddenly jump to 1 after we reach 0. That's not what we want. So let's see. Okay, to derive the CDF, I'll call it that. the general notation ft, okay? And here, t, because we know this thing could be, 1 minus this is a positive thing, right? And also this multiplying by a large constant. So I'll just say t is positive like this. And so in this case, for this t, we define it as the CDF of that an 1 minus the max less or equal than t. I write it this way. Okay. And then what is that? Let's try to simplify a little bit. It's basically 1 minus the max less or equal than t over an. And also I will, because I need to set this an myself, then it doesn't hurt for me to set it to be positive, right? I don't need to create the trouble for the sign for me. So then finally, I will have the max larger or equal than 1 minus t over an. Okay. And this is something that's similar to what we have here. When we have the max larger or equal than something, we cannot say much, right? Because it doesn't tell me where the other things smaller than it are located. Because we have known the lower bound. This is like a lower bound for the max, doesn't tell us much. But if we know an upper bound of the max, then it tells us everything. So I will write it as 1 minus the probability xn max less than this. The difference is that if I know the max is less than that, then every xi is less than that. But with the lower bound, I cannot say that. So that's why I do it this way. And again, by the same argument, I can easily write as 1 minus t over an to the power n. Okay, now this limit formula will be useful, right? So seeing this, right, because we can set an ourselves as long as an is a divergence sequence, then I could just set an to be n, right, to simplify the problem for myself. Then I have 1 minus 1 over t over n to the power n. By that limiting formula, you see, as n goes to infinity, I get 1 over minus exponential. So this is a minus sign, where we have a plus sign over there. So we have changed to plus minus exponential negative t. That's the CDF. And it's for non-negative t, right? Because you see, in order to write it this way, I do need this t to be non-negative. Otherwise, you see, this will be greater than 1, and it doesn't make any sense, right? If this constant is greater than 1, then this probability will be 0. So in other words, I need to be more specific here. So when t is greater or equal than 0, that's what we have. Okay, that's what we have. Okay, I'll just write 1 minus e to the negative t. But if t is negative, it means that this part is greater than 1, I will get 0. So to be exact, this ft as n goes to infinity, or maybe I should put here, I have the n for the CDF, but then as n goes to infinity, n goes away. So the CDF, let me see, this fnt, okay, is convergent to 1 minus exponential negative t for non-negative t, 0 for negative t. What's the CDF? What is the CDF? Actually, I think if we are familiar with some common distributions, we should be able to recognize it. It's exponential distribution. Okay, so this is the CDF of exponential 1 distribution with rate parameter equal to 1. We're done. So essentially, you see, realizing that we can set an to n, putting it back here, what we have proved is that n times 1 minus the maximum xn would converge in law to exponential distribution with rate parameter 1. Okay, and this is a very useful result. I think we have this result also from probability theory class. So what it says is that if you have an interval, okay, 0 to 1, you just you randomly find n cuts in it, okay? What it says is that here, basically, this number of cuts, okay, I should say, this number of cuts would be related to the rate, okay? And here it's about this length. So for the cut that's closest to the end, what will be the distribution of this length? And we are telling you that this length, because we know this length is going down to 0, right? But we're telling you that if you multiply this length by n to counteract this shrinkage by having increasing n, then you can stabilize the distribution as exponential 1. So that's very nice. And now I don't need to tell you how to prove it, but by intuition or sense symmetry, you can say that for this part, it's the same, right? We should have n times the minimum converge in law to exponential 1, okay? And you can prove it by what I did, but the intuition and symmetry tells us it should be the case. Okay. Do we have questions for this part? It's just a way to derive the asymptotic distribution for the extreme order statistics. I found it very interesting because for this result, we didn't use central limit theorem at all, right? We just purely derived this from probability. Okay, so now let me ask you another question. What would be your guess for this part? Let's say I call this xn minus 1. So this is the second largest, this is the largest, okay? So if I want to ask you what distribution would be this segment, that is 1 minus the second largest, what would be your guess? Yeah. Not really, not really, but I can tell you that you made a very close guess. This segment from this maximum to the end is exponential 1. Okay, of course, multiply by n is exponential 1. And this segment is actually behaving similar to this one. So this is another exponential 1. Okay, but we are going to have these two independent of each other. And by independence, the sum of two exponential 1 is actually a gamma distribution. Yeah, but we'll see that. Okay, so let me see. So we talked about this uniform 1 setting. In our second example, we'll still look at the maximum, but we change the distribution of the IID sample. Now, we don't have uniform 0 to 1, but the distribution we just have, exponential 1. So if the sample has exponential 1 distribution, then what's the asymptotic distribution of the maximum? So same question, but the original distribution is changed. Okay, so in order to show that, we still need to think about, and this is something very interesting, because this distribution, unlike uniform 0 to 1, it's not bounded. It doesn't have a maximum. So theoretically, you see, this maximum here can go to infinity, right? We cannot say that it converges to a constant. That doesn't happen. So it's more challenging. So to address that problem, we would think about doing this. Let me erase this part. So Now, we still consider this maximum to have some upper bound, right? Previously, the upper bound is 1. We know that. But here, the upper bound of it will also diverge. It can go to infinity. So let's just consider that upper bound to be some sequence Bn, which we'll find. Bn minus the maximum, okay? And we hope we may or may not, I should say, we may or may not need another divergent constant sequence here to ensure it's stable. Because it's possible that Bn, if this is divergent, minus this divergent maximum would be enough to counteract the diverge here, so that this difference is a stable, converge to a stable distribution. But we're not sure, so we still put A in here. And our idea is still to have this thing converge in law to some non-degenerate distribution. Okay, so to achieve that, we still use the CDF of this term to help us to see under what case can we have a non-degenerate CDF that doesn't depend on n. Okay, so we can have this FNT, still write that. It's the probability and here we still assume AN and BN to be both positive. And we already know BN must be divergent. For AN, we put it on hold. We are not sure. The reason is that we don't know BN minus AN is going down to 0. That's different from the previous case. We know that 1 minus the maximum goes down to 0 in that case. Okay, so for here, let's see what it is like. Again, for this one, I would have the max, okay, greater or equal than T, okay, I should say it's Bn minus T over AN. Okay. And still, we are going to say that, so pretending that this term is non-negative for now, okay, because if it's negative, then we will have this probability equal to 1, and there's no, that's not interesting. So let's assume that this is non-negative. So then we put it here. So when this is non-negative, what we would have is, and also, let me see. Yeah, what we would have is, again, to use that term, 1 minus the less than, right, and power, Bn minus T over An to the power n. Oh, sorry, what I'm doing? No. I need a CDF, sorry. I need this probability of x1 less than Bn. Okay, yeah. I'm not under the uniform case anymore. Okay, now I'm going to use this exponential one. And for this exponential one, we just saw its CDF. Its CDF function is this, 1 minus exponential negative t. Okay, so therefore, when this part is positive, non-negative, it's equal to 1 minus exponential to the power, I will say, let me see if I'm right. Right, I think so, right? So Bn minus T over An, right? So I will have to the negative of this. So it's T over An minus Bn. That's inside of it. Okay, so put it together. 1 minus exponential to the power T over An minus Bn to the power n. Okay, now the question is, I need to create something like here. Like I need a term like this, so that converges to something, a function that doesn't depend on n. Okay, so to do that, you see one thing I need to create inside in the base, right, is something with a denominator as n, because I have a power n here. So the way to do that, obviously, or one way to do that is to replace this bn, which must be divergent, by log n. So you see with that, this term would be 1 minus exponential to negative log n becomes 1 over n. Exponential t over an as the numerator. Okay. And now you can see that I almost don't need this thing, an, because I can always, so even if this an is just fixed, I can already have a limit for this. So in this case, I can just set an to be 1. It doesn't need to be divergent, okay? And then this becomes, the limit of that is 1 minus exponential to the power exponential t, negative exponential t. That's it. 1 minus that, right? I think I'm correct here. So this limit is going to here, and 1 minus stays. Right, minus 8t minus negative t. Okay, so that's it. Yeah, I think I'm correct. So in this case, I'm having this t non-negative, right? So this is the t, and the t must be non-negative by this definition. And also, what I need to have is this, right? So basically, you see this condition becomes log n minus t must be greater or equal than 0. And this is not a problem because log n is divergent, right? So for any t, I can guarantee this. Okay, so that's it. So you see, when t is greater or equal than 0, I do have this. But when t is negative, then the same issue happens again. So like the probability of having this larger than the upper bound would be 0. So that's the second part. So basically, I have this, and this distribution has an interesting name. So you see, compared to the CDF of exponential 1, this CDF has 2 exponential. One is inside the exponential function. And this function is known as what we give a name is called a Gumbel distribution. Okay. And this distribution is also sometimes referred to as the extreme value distribution. It's also that. Okay, extreme value distribution. And what it says is about the distance between log n and xn. Because you see, with this simplification, this term, it becomes, this is 1 times log m minus xn. So what I'm maximum, so I'm saying is that this difference is convergent to a stable distribution called a Gumbel distribution. So in other words, we can say that asymptotically, this xn diverges with the rate log n. That's what we learned from this result. Okay, and the Gumbel distribution also has some other uses. So it's defined because people discovered distribution and found that, okay, we can give it a name. And the Gumbel is probably the person who named it, but it's named after. And then this can be, one way to regard this is as the extreme value maximum of IID exponential 1. So we just showed that it's a way to derive it following the technique we just used. So next time when we come back on Wednesday, we will talk about how do we look at more than one extreme order statistic. So for example, if we look at the minimum and maximum together jointly, how do we derive their joint asymptotic distribution? So we'll just see a few more examples next time before we talk about our sample quanta, which will be the important part. So just as a way to, an alternative to the sample moments, the averages, the means we talk about, right? That's a way to derive a statistic, and the median and the related stuff is another way. Okay, so we'll stop here and I'll see you on Wednesday.